Hi and welcome back to what is going to be the first of a number of videos on our additional HL content on periodicity. Let's get started. In this one, we're going to look at period 3 trends as the first topic that we look at, and hopefully you will remember some of these trends from SL. When we think about period 3, we're talking about the elements that run from sodium across to argon. Okay, so these are our group 1, group 2, 13, 14, 15, 16, 17, and 18. So these all form the elements of period 3. We know a number of trends already that we've rediscussed recently. This being metallic character, the fact that it decreases as we move from left to right, remembering that we start with metallic on the left and moved to covalent non-metallic bonding. So this means that our metallic character decreases. Then electronegativity increases, first ionization energy will also increase, and atomic radius decreases. These ones essentially, electronegativity and first ionization energy, link back to metallic character because metallic character is the ability for a metal to give up an electron. So as our ionization energy increases and our electronegativity increases, it makes sense that the metallic character has decreased. And because our effective nuclear charge is increasing from left to right as well, we will see that the atomic radius is decreasing due to the electron cloud being pulled closer to the nucleus. This is also revision in that these are all the equations that you should have written down for your reactions of oxides with water. So oxides of sodium will react with water to form sodium hydroxide. Oxides of magnesium react with water to form magnesium hydroxide. Non-metallic oxides are acidic. Okay, so they will form their corresponding acids. So P4O10 will react with water to form 4 lots of phosphoric acid. Our SO3 will react with water to form H2SO4, remembering this is a major contributor to acid deposition. And then the oxides of aluminium are amphoteric because it can react with an acid or a base. So Al2O3 will react with aqueous sodium hydroxide, or it will react with hydrochloric acid. So we will form the sodium aluminium hydroxide complex, or we will form aluminium chloride. These are the trickier ones. These ones you should hopefully be more than familiar with. Remember, there is also carbon and nitrogen oxides to add into these as well. So when we talk about the physical states of the period 3 oxides, this is something that you now need to be able to talk about in HL. It pretty much follows what you would expect in that we have our oxides here. We're talking about physical states, so melting points and boiling points. We can see here that the melting points steadily increase. We have aluminium oxide and silicon dioxide forming our highest melting points here. Okay, so we tend to have high melting points in the ionic compounds, with silicon dioxide forming a covalent network lattice. Remember, this is our example of a non-carbon covalent network lattice. And then we have lower melting points as we form molecular compounds here. So these are going to be dispersion forces only in these cases for most of them, whereas we have ionic bonding and then the strong covalent molecular lattice bonding. So our ionic compounds will be solids at room temperature. Covalent network lattice, because of strong covalent bonding in all 3 dimensions, will be a solid at room temperature. P4O10 is a solid at room temperature, but then once we hit 6 and 7, so chlorines and sulfur, we see them changing to liquids and gases. There are more than one oxide of phosphorus, sulfur, and chlorine. These are still all covalent molecular, however, but they have lower melting points and boiling points, so they tend to be liquids and gases at room temperature. Remember, when we are talking about whether or not something is a solid, a liquid, or a gas and its melting point, these are physical properties. So when we look at the oxides of silicon, the key one that we need to know about is silicon dioxide, which is a giant covalent network lattice, has strong bonding in all three dimensions, covalent bonding in all three dimensions, with a very high melting point and is solid under standard conditions. It doesn't dissolve or react with water, so it remains neutral, but it can react and neutralize sodium hydroxide, meaning it is an acidic oxide. So this is the reaction of silicon dioxide with sodium hydroxide, which you should add to your notes, forming the sodium silicate and the water here. Remember, with electrical conductivity, we need to have moving charged particles. Just like diamond, silicon dioxide is not going to be able to conduct electricity because there is no delocalized electrons or no free moving ions. When we get to SO2, remember this is a covalent molecular compound. We're going to have weak intermolecular forces holding the bond molecules together with a bond angle of around 120 and a bent geometry. This gas, sulfur dioxide, under standard conditions, and it doesn't conduct electricity because it is a neutral covalent compound. This, however, is soluble in water and again is one of the contributing gases from our SOx and NOx gases that contribute to acid deposition. Okay, so SO2 will react vigorously with water to form H2SO3, which is acidic. For phosphorus, there are a number of different phosphorus oxides that tend to form interesting caged structures. There's P4O6 and P4O10. These are named by their oxidation states, phosphorus 5 oxide and phosphorus 3 oxide. They have different properties because their bonding is different. Phosphorus 5 oxide is a white powder and solid under standard conditions, whereas phosphorus 3 oxide is a waxy solid under standard conditions, so it's got slightly weaker bonding. The dispersion forces are the only intermolecular forces that hold these together, so the stronger dispersion forces are in the phosphorus 5 oxide, which is a larger molecule overall. So when P4O10 reacts with water, we form phosphoric acid. So if you can remember that P4O10 reacts with water and phosphoric, the formula for phosphoric being H3PO4, then you just balance it. You don't need to remember the coefficients because you should be able to balance it from first principles. The next in our oxides that we're looking at, moving along to group 17, are our oxides of chlorine. So chlorine forms a huge number of oxides that have a tendency to be quite explosive. We have dichlorine oxide, which is Cl2O, and this oxidized gas is easily ignited. Okay, it has a bent structure, remembering there will be lone pairs on the oxygen here, and a bond angle of around 111, so 110.9. Dichlorine heptoxide, which is Cl2O7, this really interesting structure down here, which is bent around the oxygen, but tetrahedral molecular geometry around the chlorine with these interesting 3 sets of double bonds to the oxygen. This is unstable, and you can see why that would probably be. We've got a very unusual bonding arrangement here. It's a liquid, and is held together by weak dispersion forces only because of the symmetry in the molecule. Chlorine dioxide, where we have chlorine in the middle of 2 oxygens, remembering there will still be lone pairs on the chlorine, so it will also have a bent shape, is a yellow gas that is used in paper making to essentially bleach wood pulp. This has a bond angle of around 117.6. All of these compounds are neutral covalent compounds, so they do not conduct electricity. However, when they react with water, they will form hypochlorous acid, which of course will conduct because it is an acidic solution. So the Cl2O plus H2O will form 2HClO. All of these will form the hypochlorous acid when they react with water. So if we summarize our group 3 oxides, we can have a look at their oxidation states. Okay, remembering that the oxidation states can be calculated from the formula of the oxide. We can look at their acid and base character, that group 1 and group 2 are basic, aluminium is amphoteric, and then post-aluminium we are acidic, which is the same trend that you learnt for HL. There is the empirical ratio in terms of oxygen changes as we move across with no set pattern. At room temperature, we have solids up until we hit the phosphorus waxy solids, then SO2, SO3 are gases or liquids, and Cl2O and Cl2O7 are gases at room temperature. Electrical conductivity, their physical state, and the structure of the oxide, whether it be ionic, covalent, or molecular, are all physical properties, whereas the oxidation state and their acid and base character are what we would consider chemical properties when we are asked to compare these. That sums it up for our group 3 oxides for the sodium, magnesium, aluminium, silicon. Next up, we will have a deep dive into some of the other oxides, looking at the oxides of chlorine in particular.